Okay, so highlights from chapter 1. What we're going to look at are the basic sections in chapter 1 and look at the components of a computer and how a computer is programmed. I want to emphasize the word computer initially came into English as a job title. It was a person who did computations. Specifically, the Harvard computers were women who were hired by the astronomy department to do calculations on the different data that was being taken. This was done because at the time, the late 1800s, early 1900s, women would not have a career in academia. Very few were able to get doctorates or do research, but many educated women, especially in New England, that had schools and traditions of allowing education and higher education for women, had women who had the skills to work in academia. So many were hired to do the computations for the research scientists. As the first electronic computers got built, many of the mathematical departments had women in charge of what was the computer tasks that began first using the electronic computers. In fact, the first programming language, COBOL, was developed by Rear Admiral Grace Hopper, and up until the 70s and 80s, computers were still mainly a female-dominated area of academia. As computers became more and more used in business, there was a larger push for men to come into programming. And come the 80s, the trend for women in computers changed. It's an interesting history of how computers were, as a device, were looked as being a tool and not a area of study on their own. And a lot of the women drove innovations in early computing, from Ada Lovelace, who worked with Babbage and developed the first computer programming language before there were even electronic computers. So the history is tied to the idea that computations themselves weren't as important as to what was being computed until the machine was able to do computations on such a quick level. And the modern context of computers and data analysis that we live in is bringing back the mathematical fundamentals of them on a very large scale. We live in a data world where the mathematics of computers is important. So what is a computer? A computer we can think of as connected devices. It's connected on a bus, which carries an electronic signal. The electronic signal has an identity marker or a header that routes the signal to the device. The main emphasis of computers is going to mainly be the CPU and the memory. We will be writing programs that are stored on a storage device, are loaded into memory, and then from memory, the central processing unit controls the commands. We will find the way we read input devices and the way we send to output devices is relatively universal. A change in pointing to an address will change our output from a monitor to a storage device. So when we go to write a file, it's very similar to printing to the screen initially. When we go to read from a file, it's very similar from taking input from a keyboard. The commands are structured in such a way that the device and the device drivers holds the differences between the devices. But a big focus will be putting things into memory and then running commands in the CPU that access the memory to compute on them. So the CPU is the central processing unit, and is considered to be the brain of the computer. It retrieves the instructions from memory and executes them. It's measured in speed, which is currently in gigahertz or billions of cycles per second. Now, a command takes multiple cycles to operate, but a good rule of thumb is the gigahertz of your computer is roughly, at least 4 times as many commands, 5 times as many commands. Certain commands have different cycles, how they access memory. There's timing on them, and around chapter 5, we'll look at some specifics on certain commands. Now, these commands are in binary. To us, we write binary as numbers as 0 or 1, but they are states, like switches, and the commands switch things down certain pathways. The memory is where data and program instructions are stored. Memory is a sequence of bytes, and each byte holds 8 bits. So we can talk about memory addressing, where the memory is blocked out like a post office box. And we can look at it here, how data is stored. There's an address, and then there's the byte for the address. We will see when we use things such as arrays or even strings, we tend to start counting the first item. So in this case, where it says memory address 2000 encoding for the character J, if I were referencing a string or an array that had Java inside of it, the first character would be character 0, because the way the computer accesses connected memory addresses, it looks for 2000 plus which connected piece do I want. But for us, we can think of it as a box with an address. And the CPU looks at the address and pulls out the memory content. Everything in the computer will be these combinations of zeros and ones, and it's translated by internal software or some of the libraries inside of Java. So our job is to write commands. The computer interprets those commands as zeros and ones by convention, similar to on, off, true, false. To the computer, it's a switching mechanism. To us, we can, depending on how we're going to use it, look at it as numbers of zeros and ones, or we can look at it as true and falses, or ons and offs. Now, memory itself is called volatile because when you turn off the computer, the memory goes away. Memory needs an electronic signal to be constantly applied to hold its values. To keep data between successive on and off of the device, there are storage devices. Now, this used to be tape drives, punch cards, hard disk drives, which were a magnetic medium on a platter that spun. Currently, right now, it's SSDs, or solid state storage devices, which have the ability to store memory similar to memory, or to store data in something similar to memory, but it holds its state when it's powered down. Because it needs to hold its state when powered down, storage devices tend to take longer to put things into than computer memory. Also, the computer memory is closer to the CPU on the bus, so reading from the volatile memory and writing to the volatile memory is faster. And if you progress to larger algorithms, this is something to keep in mind, that when you want efficient code, you load things into memory, process in memory, and store results on the storage device, or store large changes to storage device. The research I do in astrophysics is on a program called Milky Way at Home, and part of what we have to do is optimize how we're using memory. In fact, we need calculations to go so fast and so large, we process them through the video card, because the video card has some tailored processing for vectors because it's tailored to do a certain type of mathematical calculation. It's much quicker than general CPU. So we load our data into the computer memory and we fire it down the GPU pipeline and we pull the results back out on the other side. We don't do a lot of reads and writes to the disk so that we can process large quantities of data. And a lot of modern AI is based off of GPU calculations because of this speed enhancement. Now, output devices, generally, when we think of the monitor, the screen that we have. We'll do a quick breakdown of some things about the screen. It has a resolution, which are pixels for picture elements. They're the tiny dots. OLED screens and high resolution pixels can have many, many times the resolution of an LED screen, like most laptops or flat screens. And the spacing of the pixels determines the resolution. The actual control in making characters or windows come across goes through many layers of software. In our case, we'll be writing in Java. Java takes the commands through the Java libraries that we will access. The Java libraries process this to the Java virtual machine, and then the Java virtual machine interacts with the operating system, and we get letters on the screen. We don't have to worry about each dot to print the letter T. The software for the letter T translates it for us and writes it to the screen. In fact, we're going to rely on a lot of pre-written software that is built into the Java libraries and that are building the operating system libraries. Computers have kind of shared the resources in the form of pre-written pieces of software called libraries so that we don't have to write each pixel to the screen to get what we need to see. We will tell another program we want to see certain characters. That program has libraries that then tell the operating system what to show on the screen, and the operating system itself has drivers that then write it to the screen. So we're going to go through many layers of software that pre-exist to execute our commands and see the output. But this is the common architecture of computers right now. If you work on Linux systems, you can work on the core software that does the raw communication with the devices, or you can work higher up on what prints to your, in our case, into our Eclipse output or into your program's windowing system. Communication devices are how you connect to other computers. For a modern machine, this is mainly a wireless device. And then in that wireless device connects to a router that connects to a wide area network. And this is a very wide range of stuff if you're into networking, that there are many different layers on it. Again, communicating to those devices go through multiple drivers. And in the end, we just need to package data such that it can go to the TCP/IP stack that then goes to the network interface. So there are many layers of software that work with any of the devices that we might need to be working with, and we have loads of libraries for that help with the translation. We'll be sitting at the end of this software writing programs that work with the data itself, and then we take the data and move it to where we need to go. And so programs are known as software, or they are instructions for the computer. The reason they're called software is the physical devices have instructions inside of them, and that's called hardware. In hardware, the instructions are pre-written, etched into the silicon, drawn into the logic structure. Software then are instructions that can live in volatile memory and come and go. And this is what we tell the computer what to do with. And this is done with programming languages. In its base form, the computer reads things in machine language, which is in binary. And the CPU can translate this immediately into instructions or pathways on its architecture to run commands. And I've had to do some machine language program, especially back in the 80s when my first computer was a 2K Timex Sinclair. And sometimes the text to write the program in a higher level language filled the whole memory. If you could pre-compile your data into machine language, you could, right from the tape drive, load it into memory and have it execute from there. And so with the limited 2K of memory, sometimes we would compose our programs in machine language and load the raw numbers directly into memory and then point the CPU to start it. We won't have to do anything like that here. In fact, above machine language, there was an assembly language, which varies from processor to processor. And assembly language is a more human-readable form of machine language. In this case, we have an adding through different registers, and that gets from an assembly file. There's another program called an assembler that takes each command and turns it into the machine code. And then in the machine code gets loaded in. So it's a one step removed. And assembly tends to be a one-to-one. The command creates a machine code file, and you could write by hand a translation for them. The assembly language itself is slightly quicker to type and easier to remember. If I look at this, I can see that it's adding. I can see the two registers it's pulling from and the register that it will store the results in. Outside of assembly language, there are high-level languages. And high-level languages are more English-like. In fact, this example that we're seeing here, area equals 5 times 5 times 3.1415, is how you find the area of a circle of radius 5. We get the radius squared, 5 times 5, times pi. More human readable. To execute this then, we have to do something with the human readable part to turn it into machine language. And so if we look at some of the high level languages, we have Ada, which was named for Ada Lovelace, and it's a Department of Defense language mainly. I've also seen it used a lot in learning how to program. BASIC, which is a beginner's all-purpose symbolic instruction code. BASIC was a really big learning language in the 70s and 80s. And there were many, many programs written in BASIC, especially on like the Commodore 64s, the Atari 800s, and the 8-bit machines at the time. As 16-bit machines came about, there was a bigger push to writing in C and C++, which are the next two languages here. Now, Bell Laboratories, as the phone company, had to process a lot of data. They needed to make switching controls. If you ever look at an old movie and they had human operators that were routing cables to different ports to make phone calls work, the phone company wanted to automate this and turn it into machines, and they had mechanical switches initially. They moved to digital switching, and with digital switching they needed programs to do this. And C was one of the first languages. COBOL was the first language that was human-like that then compiled into machine code. C was probably one of the most efficient and portable ones. And oddly enough, because the phone company had a legalized monopoly from the US government, they weren't allowed to compete in the software market. So C they gave to other companies. They developed internally to be used, but then in companies like Borland, Microsoft, they were able to get the C and develop their own compilers for it. And I'll explain what a compiler is. C++, Bjorn Georgstrap decided to make an object-oriented language that was similar to C. Now, object-oriented is a way of thinking about what a program does, and as computers developed what was called threading, or the ability to run two pieces of code at once instead of one piece of code passing through the processor at one time, an object way of thinking became important. And we will spend chapter 8 and 9 really working on defining what an object is. C Sharp is a hybrid of Java and C++ developed by Microsoft. I've done some work in C Sharp. It is not one of my more favorite languages, but then I might have a slight bias against Microsoft products. I am an open source fan. COBOL is a business application language that was developed by Grace Hopper for the military. And it replaced programming in machine language and assembly. COBOL is probably one of the more lucrative languages to know well and to a deep level. There are still core machines from the 60s that are running key places that have been integrated into larger systems but have not been fully replaced. And every now and again, they need updated, and the COBOL code that is used to do their core application sometimes needs to be changed. Fortran is a formula translation language for mathematics. Java, what we're going to look at in this course, was developed by Sun Microsystems in the early 90s. It really rose in prominence with the internet. I remember Sun talking about how you could have Java on a toaster, and we all laughed. Why would you want a language that was portable enough to be on a toaster? And now I can go out and buy a fridge that has applications running on it, where I can do my grocery lists and send them to the internet. So Sun was very forward thinking in what they wanted to do. Oddly enough, some problems in Java in the 90s with security. It is not in as wide practice as they thought it would be on devices. Porting Java machines to smaller devices can sometimes be difficult, and with the rise of the iPhone and the Google Pixel, they have released very good developer kits in C++. So a lot of phones, instead of having Java, as Sun thought or hoped, they tend to have applications developed for them directly using C and C++. Java's key usage is Java code will run on any machine identically as long as that machine has a Java virtual machine on it. And so it is extremely portable, or it's easy to port to other machines. It is slowly replacing Visual Basic, which was a Microsoft developmental suite that businesses used because it was easy to use on their machines. Java got popular because businesses were starting to need more Linux and occasionally Mac machines. You could write in Java, and a Java program would run on their Mac machine, their Linux machine, and their Windows machines, while Visual Basic only ran on a Microsoft machine. Pascal was an early general purpose language, very popular in the 80s and 90s. Borland turned it into Delphi, which is the visual version of it with windowing systems. It's slowly becoming a little obsolete. It was also an educational language for a while. Python is an object-oriented general-purpose scripting language. They say for writing short programs. I've seen large programs written in Python. The Milky Way at Home project that I do my research on, we use C++ to write the code that does the mathematics. That runs on other computers. The results come back. We use Python in the back end to visualize the results. Python has a very large usage within the data science community because it has very nice visualization packages. And then Visual Basic, which was developed by Apple and then sold to Microsoft, and Microsoft really took off with it as a programming language for early Windows, while Apple went with C++ for many different reasons as their main programming language. Now, what happens is a program will be written in source code. We will be writing a lot of source code, and that needs to be turned into something the computer can understand. And so this can be done through an interpreter or a compiler. Now, with an interpreter, it takes the high-level file, reads it, and turns it into output. So interpreters have to read the source code every time they run and change it into machine code, and that takes processing. So interpreter programs run slower than pure machine code would, or virtual machine code will. And so interpreted code's really quick to write, you can put on a lot of systems, but might not be the most efficient. Outside of interpreting, you can compile source code, where a program called a compiler takes the source code, turns it into machine code. Then in that machine code file needs to be executed. And this is what C and C++ do. Java on its own right really is an interpreted language, but it has a little bit of an efficiency in it. It turns the source code to bytecode, which is a more efficient code for the Java virtual machine. So Java sits in between interpreted and compiling source code. Now, different operating systems exist. You've already heard the Microsoft Windows, Mac OS, Linux, Unix, AIX, BIOS, OS2 Warp. I'm trying to think of any other operating systems out there. Right now, the major players are Microsoft Windows, Mac OS X, and Linux's. Mac OS X is based off of Darwin, which was part of the Next Step. So it was a Unix-like operating system. If you ever have to open up a terminal in Mac, it's the same as if you were using a terminal in Linux or any of the major Unix systems. Unix systems are also Bell operating systems that they put together, and Unix, then IBM had a Unix called AIX, Sun had Sun Unix, Silicon Graphics had their Unix systems, and it was a way of organizing files. And what an operating system does is it controls the communication with the hardware. And so application programs get launched by the operating system. The operating system controls the application's program's access to memory, hardware, and other devices. So it's a layer that sits between the program and the hardware. The main part of the operating system's job is to give resources to the applications, and in Windows systems to give common interfaces. And all of this the user then acts with. So the operating system you can think of as a large collection of programs that coordinate the user and the user's application with the hardware. Why Java? I'm going to quickly jump through some of these slides. It's general purpose and it's portable. I talked about some of this. Characteristics of Java, I'm going to say that the key for us here is it's object-oriented and it's portable. The rest of these you can say of almost any other operating system. I'm going to skip through some slides here that break that down. Currently, I believe we're on JDK 18, not JDK 8, but JDK 18, so Java 18. I have to look at that. The naming conventions differ between the kits that you get, and so that's the Java Development Kit is what JDK stands for. There are different editions of it. I tend to use the standard edition. And then we have integrated development environments. NetBeans, which is Sun's development environment, and Eclipse. I'm going to do all my examples in Eclipse, but in the book we can see that there are different ways you can enter a Java program via Notepad or in NetBeans. You're free to use whatever editor you want, and if you want to compile and run from the command line, that's completely fine. I'm only going to need the .java files to do my side of things here. We'll take time to learn Eclipse. Eclipse has more features than we need currently, but it is a good tool to learn to operate in, and it's a nice way of organizing everything. Plus, if you don't have the Java development kit installed in your machine, Eclipse actually bundles the Java runtime and the development kit inside of its application. So it in itself is self-contained. Okay, that's the first lecture on Chapter 1. We'll come back in the next lecture and we'll look at some examples of Java programs.